Today, we're tackling something huge. Humanity's long quest, really, to get a unified picture of the universe. We've seen incredible progress. Newton connecting apples and planets, Maxwell weaving together electricity, magnetism, light, brilliant stuff. But right now, we're facing maybe the biggest gap in physics. General relativity, that's gravity on the grand scale, and quantum mechanics, the weird rules of the very small. Finding a theory of quantum gravity, that's the frontier. And in that spirit, we're doing a deep dive into a really fascinating what if. It's called the quantum vibrational universe, or QVU for short. It's a bold idea. What if reality at its core isn't particles, but just vibrations? So our mission today, unpack this QVU hypothesis, look at its main ideas, see how it compares to current physics, and critically, where it runs into trouble. Okay, let's unpack this. So at its heart, QVU says the fundamental bits of the universe aren't tiny points, but rather, well, vibrations.
That's the core concept, yes. And it rests on a few key postulates or ideas. First, what they call a vibrational ontology. Basically, everything is vibration. All properties, mass, charge, whatever, are just encoded in how something vibrates.
Okay, everything's a vibration. Got it.
Then there's mass vibration equivalence.
Mm-hmm.
This is crucial. Mass isn't static, it's dynamic. It's directly tied to what they call the vibration rate, or maybe intensity.
So more intense vibration means more mass.
Exactly. Higher vibration, greater mass,
Yeah.
which leads straight into their idea of emergent gravity.
Emergent, so not fundamental.
Right. In QVU, gravity isn't a basic force like electromagnetism. It arises from these vibrations. The picture is massive things, high vibration intensity, send out a kind of spherical vibration. This vibration changes the, let's call it the vibrational medium around it, and other objects just naturally follow paths that look curved through this altered medium.
Interesting, like ripples on a pond almost?
Maybe, though the medium itself isn't well defined. Another point is universal mass. They propose all particles have mass, even photons, which we usually think of as massless.
All particles, including light. Why?
They suggest this non-zero mass is why photons have a finite speed and carry momentum. We'll definitely need to dig into that one later.
Okay.
And finally, vibrational merging. When things interact, their vibrations somehow average together. They form a new thing with a new average mass.
Average together. Okay, so stepping back, what does this mean for you, the listener? It's a whole different way to think about mass. And gravity, it touches everything.
It really does. And this core idea, mass is vibration, it does resonate conceptually with Imsi Han, doesn't it? Mass is concentrated energy. QVU tries to give a mechanism for that energy vibration.
And it's not totally out of left field, right? You mentioned there's some history here.
Well, yes, surprisingly.
All right.
It echoes ideas from the very beginning of quantum theory. Back in 1924, Louis de Broglie.
The wave particle guy?
That's him. In his PhD thesis, he proposed that any particle with rest mass, m-lor, has an internal clock, some kind of periodic phenomenon happening inside it.
Right.
And its frequency is directly linked to its mass by higher of man. That's the Planck relation.
Mm-hmm.
We now call this the Compton frequency.
Wow. So even back then, there was this idea of particles having an internal rhythm tied to their mass. QVU isn't just pulling this from nowhere.
Exactly. It taps into that lineage.
Mm-hmm.
But here's the first big hurdle. What does vibration rate actually mean? Frequency, amplitude,
Energy.
energy.
It needs to be precise.
Absolutely. And if it means frequency, like de Broglie suggested, we hit a problem immediately with how oscillators work in physics.
How so?
Think about a simple pendulum or a mass on a spring. The heavier the mass, the slower it swings, right? Lower frequency.
Right.
Same basic idea holds for quantum oscillators. Mass is typically inversely proportional to frequency. So if QVU's vibration is a particle oscillating in some field, higher mass should mean lower frequency.
Which is the exact opposite of what QVU claims, higher vibration, higher mass.
Precisely. So for QVU to work, the vibration can't be like a pendulum. It has to be intrinsic to the particle itself, an inherent property.
Ah, okay. So the particle is the vibration in a sense.
Yes, that shifts much closer conceptually to something like string theory, where different particles are different vibrational modes of a fundamental string. Higher energy mode, higher mass.
Okay, that makes more sense. The vibration has to be the particle's internal energy state, not it shaking around in space.
Exactly. That aligns it better with de Broglie and EMCA.
All right, critical distinction. Now, let's pivot. How does this QVU picture stack up against our reigning champion of gravity, General Relativity? GR says mass and energy curve space-time itself.
Yes, and the key thing in GR is what causes that curvature. It's not just mass. It's something much richer. The stress-energy tensor, T.
T. Sounds complicated.
It is. It's got 10 independent components. TA is energy density. That includes mass.
Mm.
But you also have TA, which is momentum density, how energy flows. And T terms for pressure. T for shear stress.
Whoa. So it's not just how heavy something is, but also how it's moving, what pressure it exerts. All that bends space-time?
All of it contributes, yes.
Mm-hmm.
And this is where QVU runs into a fundamental mismatch, a big one.
Okay.
It's a scalar versus tensor problem. QVU's spherical vibration spreading outwards. That sounds like a scalar field. Gravity described by just one number at each point, like temperature or density.
Simple.
Too simple, perhaps, because GR's source, the stress-energy tensor, is far more complex. A scalar theory just can't capture the effects of momentum, pressure, or stress on gravity. It only responds to the energy density part.
Can you give an example where this difference shows up?
Absolutely. Frame dragging, the lens-Thirring effect.
We're spinning things drag space-time.
Exactly. GR predicts that a rotating mass, like Earth or a black hole, literally twists space-time around it. This effect comes specifically from the momentum density terms in the stress-energy tensor, the TO components, and we've measured it. Gravity Probe B confirmed it.
Okay, so GR predicts it. We've seen it. What about QVU?
QVU, being scalar, based only on vibrational intensity or mass, has no way to produce frame dragging. It would predict zero difference between a spinning planet and a non-spinning one of the same mass. That's flat out contradicted by experiment.
So that's not just a small detail. It's a major failure to match observation.
It's fundamental. It shows QVU, as described, can't reproduce key gravitational physics we know is real.
So for you listening, the point is QVU isn't just a different lens on gravity. In this respect, it seems like a step backward from what we already know works really well. Now, you mentioned string theory earlier. That's another big contender for quantum gravity, also based on vibrations. How do they compare? Similar ideas, different execution.
There's definitely that shared starting point. Particles aren't points, they're vibrations, and mass comes from the energy of that vibration. Both aim for a unified picture, but the differences are huge. First, the graviton. String theory naturally predicts a particle that mediates gravity, the graviton, and it has the right properties. Massless, and crucially spin 2.
Spin 2. Why is that important?
Spin determines how a particle interacts. A spin-2 mediator is what you need mathematically for gravity to couple to the entire stress-energy tensor, not just mass. It fits perfectly with GR.
And QVU.
QVU's spherical vibration implies a spin-0 mediator, a scalar particle. That just doesn't work for gravity as we observe it. It clashes fundamentally with GR's success and string theory's prediction.
Okay, so mediator mismatch. What else?
The whole mathematical structure.
Mm-hmm.
String theory is this vast, highly developed mathematical framework. It needs extra dimensions, specific geometries.
Mm-hmm.
These things aren't just tacked on, they determine the properties of the particles, the vibrations.
And QVU.
QVU, what doesn't have that?
Yeah.
There's no specified medium for the vibrations, no mention of dimensions, no underlying equations dictating how things vibrate. It's missing the entire mathematical engine.
So it's like QVU sketched a cool concept car, but string theory actually tried to build the engine, the chassis, everything, even if it's not street ready yet.
That's a fair analogy, yes.
Okay, let's bring in another giant. The Standard Model of Particle Physics. Hugely successful, describes all known particles and forces except gravity. Any new theory about mass has to deal with the Standard Model, right?
Absolutely, and the Standard Model has its own very specific story about mass. The Higgs mechanism.
The Higgs boson, the God particle nickname.
Right. The idea is there's a universal Higgs field. Most fundamental particles are actually massless at high energies. They acquire mass by interacting with this field. Think of it like wading through treacle. Some particles interact strongly, they get a lot of mass like the W and Z bosons or the heavy quarks. Others interact weakly, they get little mass like the electron.
And some don't interact at all?
Exactly. Photons and gluons don't interact with the Higgs field because of certain symmetries, so they remain massless. The Higgs mechanism explains this whole hierarchy, this vast range of masses we see.
Okay, so the Standard Model has this detailed, specific process involving the Higgs field. How does QVU's single idea masses as vibration rate handle all that variety? The huge difference between electron and top quark mass, the massless particles.
Doesn't really. QVU just says different particles have different vibration rates, but it gives no reason why. Why is the top quark's vibration rate so incredibly high compared to the electrons? Why would photons or gluons have a zero rate?
So it just replaces one question with another?
Precisely.
Yep.
It replaces why this mass with why this vibration rate.
Yeah,
It's a relabeling, not an explanation. It lacks the predictive power of the Higgs mechanism.
that seems like a pretty major gap, which brings us to some really critical hurdles for QVU. Let's start with that photon mass idea. QVU explicitly says all particles have mass, including photons. Seems simple, but you said big consequences.
Enormous consequences. Because in the standard model, specifically QED quantum electrodynamics, the photon must be exactly massless. It's not just a preference. It falls directly out of a fundamental principle called gauge invariance.
Gauge invariance again. Why does that demand a massless photon?
It's deep, but basically, gauge invariance is a symmetry that ensures physics looks the same even if we shift our mathematical potentials in a certain way. It's linked to fundamental conservation laws, like charge conservation. If you try to add a mass term for the photon into the equations, it breaks gauge invariance. It's mathematically forbidden if you want QED to work as spectacularly well as it does.
Okay, so theory says no. What about experiments? If photons did have mass, what would we see?
We'd see several things, none of which we observe. First, the speed of light wouldn't be constant. It would depend on frequency. High-energy gamma rays would travel faster than low-energy radio waves.
So light from a distant supernova would arrive smeared out. Blue light first, then red.
Exactly. But we don't see that. Light across the spectrum from distant events arrives essentially simultaneously. That puts incredibly tight limits on any frequency dependence. Astronomy would look completely different.
What else?
A massive photon, being a spin-1 particle, would have 3 possible polarization states. We only ever observe 2 for light, transverse polarizations. That third, longitudinal state, ever seen. And finally, electromagnetism wouldn't have infinite range. The standard inverse square law relies on a massless photon. A massive photon leads to a Yukawa potential. The force would drop off exponentially over some distance. Galactic magnetic fields wouldn't extend the way they do. The universe would be structured differently.
Wow. So theory forbids it, and observation shows no sign of these effects. How massive could the photon possibly be then?
The experimental limits are astonishingly small. The particle data group quotes something like 10 Ural electron volts. That's ridiculously tiny. Some theoretical limits based on cosmic magnetic fields push it down even further, towards 10 Euro-kilograms.
Practically zero.
For all intents and purposes, yes. And for theoretical consistency within the standard model, it is 0. So QVU's claim that the photon has mass flies directly in the face of both solid theory and overwhelming evidence.
That's a huge hurdle, almost a showstopper.
It's certainly one of the most significant challenges, yes.
Okay, another point you flagged earlier was this generator-participant problem. Can you explain that?
Sure. The idea in QVU is that massive objects generate gravity via their vibration. But then it also says photons, which it claims have mass, are affected by gravity. They follow curved paths.
Right. So,
Well, in established physics, like electromagnetism, the property that generates the field, charge, is also the property that determines how something responds to the field. Charge creates E-fields. Charge feels forces from E-fields. If mass, or vibrational intensity, is the source of gravity in QVU, then shouldn't all things with mass both generate gravity and respond to it equally? Why would photons only be responders, not generators, or very weak ones? It seems inconsistent.
I see. It implies two different roles for mass, or maybe something else is needed.
Exactly. To fix this, QVU might need to introduce another property, maybe called vibrational charge, which determines how strongly something generates gravity, distinct from its mass, vibrational intensity.
But that adds more complexity, right? Another unexplained property.
It does. It solves a logical inconsistency, but raises new questions about what this new charge is and why it correlates with mass.
Okay, let's tackle the vibrational merging idea. Objects combine, their vibrations average together. Sounds a bit strained.
It is strange, especially when you unpack it. First, to be clear, this has nothing to do with the term used in quantum chemistry. Mechanically, it sounds a bit like a perfectly inelastic collision things stick together. Momentum is conserved, but kinetic energy usually isn't.
Okay.
But here's the massive problem. Conservation laws. If vibration rate corresponds to mass, and these rates simply average when two identical objects merge.
Wait, average. So if two things, each with mass m, merge, the result has mass m, not 2m.
That seems to be the implication of averaging. The final mass would be half the total initial mass.
That violates conservation of mass energy hugely. Where does half the mass energy just go?
Exactly. It's a catastrophic violation of one of the most fundamental, best-tested laws in all of physics. The theory offers no explanation for this massive energy loss.
And is that averaging even how quantum things combine?
Not at all. Quantum systems superpose, they interfere, wave functions combine in complex ways. They don't just average their properties like mass or charge arithmetically. It's fundamentally non-quantum mechanical.
So this merging idea isn't just fuzzy, it seems to break fundamental physics. Energy conservation is pretty non-negotiable.
It's about as bedrock as it gets. This is another profound issue for QVU.
Okay, so we've seen a lot of challenges. What would it actually take for QVU to move beyond just an interesting idea, to become a real scientific theory?
Math. Rigorous mathematics. Specifically what physicists call a Lagrangian formulation.
A Lagrangian?
It's the standard way modern physics works. You write down a mathematical function, the Lagrangian, that encodes the dynamics of your system, its fields, particles, interactions, symmetries. From the Lagrangian, you derive the equations of motion. It's the engine of the theory.
So QVU needs its own Lagrangian.
Absolutely. Proponents would need to define precisely what field represents vibration. Is it scalar, vector, tensor? They'd need to specify the symmetries it obeys, especially how it handles gauge invariance if the photon is massive. Then they'd have to write down the actual Lagrangian terms, kinetic, potential, interaction.
That sounds like a huge undertaking.
It is. And there's another deep issue. Background independence.
Meaning?
General relativity is background independent. Space-time isn't a fixed stage. It's dynamic. It evolves with the matter and energy. QVU, as described, seems to assume a fixed background, some pre-existing medium where vibrations happen.
Like the old idea of the ether.
Somewhat analogous, yes. Most physicists see relying on a fixed background as a step backward, especially for a fundamental theory of gravity. It limits its ability to describe cosmology, the universe as a whole.
So a full mathematical framework is step one. What else? A theory needs to be testable, right? Make predictions.
Crucial. It needs to make unique, quantitative, falsifiable predictions. Things we can measure that would show QVU is right, and, more importantly, potentially show it's wrong.
What might those predictions look like for QVU?
Well, if it insists on a massive photon, it needs to predict a specific mass value. That value would then predict a specific time delay for different frequencies of light from distant sources, like gamma ray bursts. We could look for that exact delay.
Testable. What else?
If gravity is truly scalar, as QVU implies, it might predict different properties for gravitational waves than GR does. GR predicts two polarization modes. Scalar theories can allow others, maybe up to 6. LIGO, Virgo, KHRI could potentially test that.
Okay, GW's particle physics.
For particle physics, QVU needs to do more than just say vibration rate equals mass. It needs a formula or a mechanism derived from its Lagrangian that calculates the masses of known particles. Why is the muon 200 times heavier than the electron? QVU would need to predict that ratio from first principles.
Taller.
Indeed. And finally, that vibrational merging problem. If it really does lose energy, QVU needs to predict how that energy is lost. Is it emitted as new particles? A specific spectrum of radiation, something we could actually search for during mergers.
Right. Without those kinds of specific measurable predictions, it just stays an idea, not science.
Precisely.
Okay, let's wrap this up. Looking back at our deep dive into the quantum vibrational universe, it definitely starts with an appealing, intuitive idea, doesn't it? Mass is vibration. It feels simple, fundamental. And we saw it echoes some early quantum ideas from de Broglie, even has conceptual links to string theory.
It does have that initial philosophical appeal, but as we've unpacked it, the challenges are really significant. There's the fundamental clash between its implied scalar gravity and the tensor nature of GR, highlighted by things like frame dragging. That's huge.
Yeah.
Then the massive photon postulate flies directly against gauge invariance and mountains of observational data ruling out those effects.
Another big one.
Plus, the undefined nature of the vibration, the serious energy conservation problems with vibrational averaging, the complete lack of a mechanism to explain the known particle mass spectrum.
And the lack of a mathematical framework, the background dependence.
It's a long list.
It really asks a profound what if about reality. But as you can clearly see, going from a cool question to a full working predictive theory of physics, that's an incredibly steep climb.
It is. It requires turning those intuitions into hard math, turning concepts into equations that respect conservation laws, and turning speculation into predictions you can actually go out and test.
So this deep dive into the QVU really highlights the ambition of physics, but also just how high the bar is set for any new idea that wants to truly change how we see the cosmos. It leaves us wondering what other what-ifs are out there, and for you, what further questions does this raise about what mass really is, or the fundamental nature of space-time itself?